The purpose of this video is to discuss some of the methods of estimating light aircraft takeoff performance as it relates to density altitude, and to provide an introduction to the KochChart software, a free educational software tool that automates the calculation of takeoff and rate of climb performance estimates. I'll put a link in the description below for downloading the software. It is currently only available for Windows 32-bit and 64-bit computers. Also, it is a standalone executable file, meaning all you need to do is download the file to whatever directory you prefer on your computer, then double-click the icon to run it. There is no installation file. This is what the KochChart software interface looks like, but before we get into running the software, let's review what the KochChart is, shown on the right in this image, what it does, and some other methods used to estimate takeoff and climb performance. First, a disclaimer: this is only an educational tool and not to be used for actual flight planning. While this pub is coming up on 17 years old now, it is still on the FAA's and the NTSB's websites. The FAA pamphlet recommends using the Koch chart for making approximate temperature and altitude adjustments when the AFM or POH is not available. So it may still be useful today to understand this chart. As a historical aside, you can see an early version of the Koch chart from 1964 in the 1965 revision to FAA Advisory Circular 6111, although it is a much less conservative version than the one described in this video and used by the Koch Chart program. That version was rescinded and a corrected version was issued by the FAA in 1967 as Advisory Circular 6137. In that same circular, the FAA recommended using their newly developed DENALT Performance Computer. DENALT is a witty contraction for density altitude. It is a whiz-wheel style computer that will be discussed later in this video. The Koch chart shown here is really a nomograph that, with a ruler and a pencil, calculates density altitude behind the scenes, so to speak, to give you takeoff and rate of climb performance information. In this case, nomograph refers to a tool that, when you pick points on the outer two axes and connect them with a line, the center axis gives you the answers you want. The very nonlinear middle vertical axis for the takeoff distance and rate of climb is merely applying a factor to the calculated density altitude, with the station temperature in degrees Fahrenheit on the left vertical axis and the station pressure altitude on the right vertical axis as inputs. Recall that the pressure altitude can be found by setting your altimeter to 29.92 inches of mercury or 1013 millibars and reading the indicated altitude. Now, I said this is actually a density altitude calculator, so let me show you what I mean. Here we modified a Koch chart, removing the middle axis and replacing it with a linear density altitude scale. If we choose standard day sea level conditions, as shown in the red text on the left, we can set the 0 point of our nomograph scale. And by picking other conditions and calculating their density altitude, we can set the tick marks on the scale. Note that the Koch chart program uses the National Oceanic and Atmospheric Administration, also known as NOAA or NOAA. It uses their simplified method for calculating density altitude. So at standard day conditions, the program calculates a density altitude of 17 feet, not 0. But we use NOAA's method to be consistent with ForeFlight's and probably others' calculation of density altitude. But obviously there are other than standard day conditions that can give us a density altitude of 0. For example, here in green is another condition that gives us a density altitude near 0. A cold day in Wichita, Kansas. By the way, NOAA has an online density altitude calculator you can use to verify these numbers. I'll put a link to it in the description below. Also, all of the density altitude numbers in this video assume dry air. In the program, you can simulate this by deleting the dew point or by setting it to a very low number, -40 for example. Humidity has the effect of increasing the density altitude sum, and the program uses the temperature and dew point to capture this effect. Here's another density altitude case from my home airport, Meadow Lake. With an elevation of almost 6,900 feet, it doesn't have to get too warm before the density altitude gets to be a real concern. The conditions shown here result in a 10,000-foot density altitude. Lake County Airport in Leadville, Colorado, the highest elevation airport in North America, is even worse. At almost 10,000 feet elevation, it has to be a very cold day to keep the density altitude at or below 10,000 feet. So now that we've established that the Koch chart is at its base a density altitude calculator, how did Koch decide what the effect of density altitude would be on takeoff performance and rate of climb? So far, I have not been able to come up with his original paper that would shed some light on this, but we can see that he envisions a nonlinear relationship. By the way, if you have Koch's original paper, please let me know in the comments. If we superimpose Koch's scale on our density altitude scale, we can back out the relationships he used. Setting aside the rate of climb issue for now, let's look at how Koch saw density altitude's effect. If we pick points off the Koch scale and compare them to our density altitude scale, we can generate a curve. Here we have a plot of such points. We can see that Koch doesn't see density altitude as having a linear effect on takeoff distance, as the graph gets steeper and steeper as density altitude increases, which means our takeoff run is getting longer and longer. Others have also generated tools and rules for the effect of density altitude on takeoff distance. Let's look at 3 of them. Sparky Imeson, in his book, The Mountain Flying Bible, suggests adding 12% to your takeoff roll for every 1,000 feet of density altitude up to 8,000 feet, then adding 20% for every 1,000 feet after that. These percentages are for an aircraft with a fixed pitch propeller and are added to your handbook or POH value for standard day sea level performance at your current takeoff weight. You can see that it is slightly conservative up to about 3,000 feet compared to the Koch chart, but above 3,000 feet, the Koch curve imposes an increasingly higher takeoff distance penalty. For airplanes with a variable pitch propeller, Imeson says to add 10% to your takeoff roll for every 1,000 feet of density altitude up to 8,000 feet, then add 15% for every 1,000 feet above that. You can see that an aircraft with a variable pitch propeller or constant speed prop is penalized less than the fixed pitch propeller equipped aircraft. This is because the constant speed prop can adjust its pitch to take a bigger bite out of the less dense air. I don't have the FAA's original DENALT WizWheel computer, but it appears the FAA passed it off to a contractor at some point. I do have the 1989 Aero Products Research version, shown here, which, unlike the FAA version seen earlier, which had separate WizWheels for fixed and variable pitch aircraft, the Aero Products version has scales for both types of aircraft in the same device. Here the brown line is a curve fit to data read from the DENALT computer for fixed pitch, and here we add the DENALT computer depiction for variable pitch. As a fourth estimation method, we add James Embree's rules of thumb to the chart. For the fixed pitch case, he recommends adding 15% for every 1,000 feet of density altitude up to 8,000 feet compared to standard sea level performance, and 20% for each 1,000 feet above 8,000. However, the 20% is multiplied by the performance you calculate for 8,000 feet density altitude, so the calculation is slightly more complicated. As with Imeson and the DENALT computer, Embree has a different calculation for the variable pitch case. Add 12% for each 1,000 feet of density altitude up to 6,000 feet relative to standard day sea level performance, and add an additional 14% for every 1,000 feet above 6,000. However, similar to the fixed pitch case, the additional 14% is applied to the takeoff distance calculated for 6,000 feet density altitude, not your standard day sea level takeoff distance. Now let's compare these estimates to some actual handbook values. Here we add some data points from the 1978 Cessna 172P manual. The Cessna 172 is a fixed pitch propeller aircraft. Notice that the points follow the Imeson line for fixed pitch fairly well. And here we add data points, the magenta circles, from a Piper Cherokee Warrior 2 manual from 1976. The Warrior is another fixed pitch propeller airplane. You can see that the points almost exactly follow the Embree and the DENALT lines for fixed-pitch propeller aircraft. Finally, we add some data points from a 1968 Cessna 182L. The Skylane has a variable pitch propeller. And let me make a comment on all these comparisons. It's very important to note that while all these estimation techniques will allow for calculation beyond the limits of these flight manuals, which end between 7,000 feet and 8,000 feet for the Cessna and Piper manuals shown here, going beyond published data is not recommended and may not be legal. While we won't review it here, all of the 4 techniques also have recommendations for estimating the reduction in rate of climb based on density altitude. Again, these percentages are applied to your published sea level standard day rate of climb performance at your current weight. The Koch Chart computer program calculates these percentages as well. In summary, the Koch chart is a nomograph that calculates a density altitude based increase in takeoff distance and decrease in rate of climb performance. The inputs to the Koch chart are station temperature in degrees Fahrenheit and station pressure altitude, which may be found by setting your altimeter to 29.92 inches or 1013 millibars. Also, we looked at other means to estimate takeoff and climb performance based on density altitude, and they include those of Imeson and Embree and the DENALT computer. The Koch chart software calculates values for the 4 methods shown here, so let's take a look at the program now. When you click the link to download the software, you'll be taken to a page that looks similar to this one. The version number might be different. You should see the latest up here, should say latest. And if you have a 64-bit Windows installation, you would choose this 64-bit file. And if you have a 32-bit Windows installation, you would choose this one that says x86. And once you download the software, you can download it anywhere on your computer you want. Just remember where you put it, and that will put an icon at that download location that we can use to open the software. Now that you have the icon for the executable file, you can double click on it to launch the program. The first thing you'll see is this disclaimer, which we talked about, and that just says that this is not a flight planning tool. This is an educational tool to understand the effects of density altitude on takeoff distance and rate of climb. If you agree, you can accept, and then the main window for the program will open up. In general, blue boxes are required inputs, while the green boxes are values that the program calculates and displays to you. At the top, you see the version number. Then there's a menu bar with a file menu, which lets you look at stations that you've recently looked at the weather for. And also there's an exit button to leave the program. On the help menu item, there's an about button where you can find some information on the program, including where it gets some of its data. And then at the bottom down here, there's an email address if you want to report any bugs or have any comments or questions. Also on the help button is a check for updates selection, which will allow you to check to see that your software is the current software. If it's not, it will take you to a page where you can download the latest software. And there's also a KochChart on YouTube button here, which leads to this video that you're watching right now. There are 5 tabs on the software: the Koch Chart tab, which we're looking at now, the Imeson tab here, the DENALT tab, and the Embree tab. Finally, there is the Compare tab, which allows you to see those graphs that we looked at earlier in this video. And once we calculate a density altitude, a red line will appear on both of these graphs to compare the different methods to each other. So starting with the Koch tab, the first thing I would recommend doing is put in your standard day sea level takeoff and rate of climb performance, which comes from your airplane flight manual or pilot's operating handbook. I'm going to put in 1,200 feet for my takeoff distance and 850 feet per minute for my rate of climb. The next thing you'd want to do is choose a station ID of the airport that you're flying out of. I'm going to choose my home airport, Kilo Fox Lima Yankee, Meadow Lake Airport, and click Get METAR. Provided you have an internet connection, the program will go out and get the weather for your airport if it collects weather. And you can see that that has populated this box. But more importantly, it has populated these top 5 blue boxes with the information needed to calculate pressure altitude, relative humidity, density altitude. Those numbers are fed into the Koch chart, and you can view the Koch chart by clicking the Plot Koch Chart button. So here's the current Koch chart for Meadow Lake Airport. You can see that the station temperature here in degrees Fahrenheit is on this axis of the Koch chart, while the pressure altitude in feet is here on the Koch chart. When you connect those two with this red line, you get the percent you need to add to your takeoff distance and the percent you need to subtract from your rate of climb. Those numbers are here and here. Those can be multiplied times our sea level standard day takeoff distance and rate of climb to give us the Koch takeoff distance here and the Koch rate of climb here. If you'd like to see those graphically compared to your sea level performance, you can click Show Bar Graph, and you'll get a bar graph comparing the Koch takeoff distance to your standard day takeoff distance, as well as the Koch rate of climb compared to your standard day sea level rate of climb. You can see we've taken quite a hit on both. Our rate of climb has been decreased to 289 feet per minute, and our takeoff distance is way out here now at almost 3,000 feet. So the Koch tab is the simplest tab. If you wanted to compare Koch charts for 2 airports, you can just type in a different station ID here. We can type in Denver, for example, and all the numbers are recalculated. We can plot another Koch chart, and we can compare the two. Notice that there's an overlay on each chart that includes the station identifier, so you can see which Koch chart goes with which airport. Also, you can do a what-if exercise. Say you're going to be flying out of Denver later today when you know the temperature is going to jump 10 degrees centigrade. You can change this 14 to a 24, hit recalculate, and plot a new Koch chart for those conditions. And you'll also get the new Koch takeoff distance and the new Koch rate of climb. So I'm going to go put my home airport information back in here. In fact, I'm going to use the recent stations menu, just because I can. And now we're going to look at the Imeson tab. And remember, what we're doing is we're applying density, altitude, and rate of climb rules of thumb developed by different people. They're all compared on this last tab, which draws, once we've calculated density altitude, we get this red vertical line on our charts. And you see this is for a density altitude of 8113, which if we look at our Koch tab, that is correct. It's 8113. So you can see how the different methods will give you different takeoff distances and different rates of climb. So back to the Imeson tab. Imeson, if you'll recall, gave us a choice of whether to calculate fixed pitch propeller performance or variable pitch propeller performance. I'm going to choose variable pitch. And before I hit calculate, notice that our standard day sea level numbers have been copied from the Koch tab, as well as the density altitude. And here are our Imeson takeoff distance and rate of climb. If we want to compare those to the Koch numbers, we can just hit show bar graph and we can see the rate of climb and takeoff distance comparisons. You'll notice this is a much shorter takeoff distance for Imeson, and that's largely because we chose variable pitch propeller. Koch doesn't give you that option. And if we look at the compare tab, we can see that our Koch number is way up here, while our Imeson variable pitch number is way down here, and that shows up when we plot on our bar graph. Now, Imeson also has corrections that we didn't talk about earlier, and those are corrections for wind, runway slope, and runway surface. So we can correct our density altitude takeoff distance for these things. And where I would recommend starting is this wind calculator at the bottom of the tab. You'll notice that here at the bottom of our tab, we have the METAR that we collected for Meadow Lake Airport, and it has automatically populated the winds box here. Now, METAR winds are given in true direction, so we've got winds of 190 at 12, gusting to 21. If we apply the magnetic variation to that, and this is the magnetic variation for Meadow Lake, which this has been automatically pulled from an FAA website. Then we get these magnetic winds, 183 at 12, gusting to 21. Now we have to choose what runway we're going to use so we know what our wind components are. If we don't know the runways at this airport, and click Show Runway Info, and the program will go out to another FAA website and get the runway information. I'm going to choose runway 15, so I'll put 15 in the runway number box here and hit enter. I could also hit this calculate button here, and you'll see it has calculated a headwind, there is no tailwind, and a crosswind. So it's broken our wind up into components. It has also automatically populated our headwind tailwind box up here and automatically checked the headwind box. One thing we need besides the wind to calculate our factor for takeoff is the rotation speed of our airplane, because the Imeson correction uses a ratio of the headwind to the rotation speed. I'm going to use 55 knots for my rotation speed. For runway slope, I happen to know that runway 15 at Meadow Lake slopes downhill 1.4 degrees. So I'm going to put that in here. And my runway surface is hard and dry. But just to show you a correction for a different runway surface, I'm going to put in firm turf. Now that we have all these boxes populated here, we can hit calculate and we can see the Imeson corrections applied to the Imeson density altitude takeoff distance here, and the Imeson corrections applied to the Koch takeoff distance to the right. So for example, we started with 2,180 feet takeoff distance for the Imeson density altitude, and that was derived from our original takeoff distance at sea level of 1,200 feet and factoring in this density altitude of 8,113 feet. Now applying the wind correction to that, our 2,180 feet is reduced to 1,560 feet because of our 10-knot headwind. Our 1.4 downhill runway slope reduces our takeoff distance further to 1,450 feet. And then the fact that we're taking off on turf and not a hard surface increases the distance slightly to 1,550 feet. That's our Imeson takeoff distance with corrections. Those same corrections were applied to our Koch takeoff distance, and that results in a Koch takeoff distance of 2,100 feet. If we want to compare those, we can do it on a table, or we can click on our Show Bar Graph button again, and we can see it on a graph. Our rate of climb information hasn't changed here. Here's our density altitude corrected takeoff distances. And in this top part of the chart, we have takeoff distances that have been also corrected for wind, runway slope, and runway surface. Now that we've done the work of populating the Imeson tab, it's all downhill from here. The DENALT and Embree tabs are automatically populated using the information we've provided so far. So if we click on the DENALT tab, everything's already done. We have our standard day conditions here that we put in on the Koch tab. We have our previously calculated density altitude, and we have our DENALT takeoff distance and rate of climb, as well as the DENALT takeoff distance corrected for wind, slope, and runway surface. Clicking on our Show Bar Graph button, we now add the purple bars, which are for the DENALT flight computer. Similarly, the Embree tab is done as well because we've given it all the information it needs. And we can compare the Embree numbers on the bar graph, and they're the orange bars. I also want to show you that for some runway surface conditions, rather than just applying a factor, like for example, for a firm turf runway, I believe the Imeson correction adds 7%. For a soft field condition, there's actually a range of factors that are applied. So if I choose soft field here and calculate, you'll see that we get a range of takeoff distances. And the way that looks when you plot it on the bar chart is like this. Here in the middle of the chart, again, these are only corrected for density altitude. Looks like I need to click on the DENALT tab so that I'll get a bar here. So here's what it looks like if we choose soft field for our runway surface. Recall that these bars in the middle are the takeoff distances corrected only for density altitude, while these bars at the top have been corrected for density altitude and wind, slope, and runway surface. And you can see that each of these bars has a range now for the takeoff distance. For example, for the Imeson takeoff distance, we have a range between 1780 and 2530, and that's just based on the Imeson rule of thumb for a soft field takeoff. So now you've seen most everything this program does. Remember that if you have any questions or comments or bug reports, there's an email address on the Help About menu, and I hope you enjoy using the program.